Okay, so I hope everybody had a really good week. Having a good May so far. So today we're going to mostly finish up our main trigonometry unit. We'll do for the last, class will meet, I think, 3 more times after today. And so we'll do some more, we're going to do some more kind of applications of trigonometry after today. But today is going to be kind of the end of the pure trigonometry unit. And we're going to do what I think is a fun exercise in trigonometric modeling. Some people who were in the program already right at the beginning in 2021 may have seen this already, but hopefully it's been a long time, so it may at least feel fresh to you. Okay, so welcome everybody as always, and thank you for coming, and thank you for your patience with the data distribution. Okay, so like usual, I want to start with going over the homework. So there were only 2 homework problems, so it won't take that long. And let me mention even before the homework. So if you remember what we did last time, oh yeah, and also please write your name in the chat so I have your record for attendance. And so if you remember last time we talked about the law of cosines and the law of sines. And in both cases, we had a triangle that was labeled with the vertices were labeled capital A, B, and C. And then the opposite sides are labeled lowercase a, lowercase b, and lowercase c. So the convention is you always use the lowercase letter opposite the vertex with the same uppercase letter. Okay? And so the law of cosines was basically a version of the Pythagoras theorem, right? But instead of c squared equals a squared plus b squared, you have this extra term, this minus 2ab cosine c. And this extra term is what makes the law of cosines work for any triangle and not just a right-angled triangle, right? So you need this extra term if you want it to work for every triangle. So we had this formula last time. And then the law of sines was a little bit different, but it said that the ratio of a side of a triangle to the sine of the opposite angle, so little a over sine big A, is the same no matter which side you use. So little a over sine big A is the same as little b over sine big B, which is the same as little c over sine big C. Okay? So these were the law of sines and law of cosines. And both of the problems on the homework are practiced with the law of cosines. Okay? So let's look at the law of cosines over here. So here for homework exercise number 1, we have that 2 sides of a triangle have length 2 and 3. So maybe this is 2, this is 3. And then the angle between them is 30 degrees. So this is a pretty straightforward law of cosines problem. And we have this other side of the triangle, C, and we want to determine the length of C, right? So using the law of cosines, what equation can we set up that is an equation involving C that we'll be able to solve for C?
Okay, let's say c squared is equal to c squared is equal to a squared
right
plus b squared
minus
minus 2ab cos c.
Exactly. So this is great. Okay, so now what do we plug in here?
Let's say a is equal to 2 and b is equal to 3.
Great. So 2 squared plus 3 squared.
So 2 squared plus 3 squared is equal to 2 minus parenthesis open, or let's say 2 times 3
Right.
cos 30 degrees.
Exactly. Okay, so that's 4 plus 9 minus times 2 times 3 is 12. And then cosine of 30 degrees is
root 3 or 2.
Exactly. Right. So this becomes 13 minus 6 times square root of 3, right? And so what is the problem asking us to find? So this is perfect. So this is c squared equals 13 minus 6 square root of 3. So, but what we need to find is we need to find c, right? So in the end, we don't want just c squared, we want c. So to find c, we have to take the square root. So square root of 13 minus 6 square root of 3. And when you get an answer like this, if you have a calculator, you should check to make sure that your answer looks reasonable from the picture. So if I do the square root of 13 minus 6 times square root of 3, that, oh, hello? Sorry. Okay.
You know my door again.
Okay. So
Sorry.
remember, sorry, if you're not asking question, please mute yourself. Thank you. Okay. So okay, right. So this is what we have, and it turns out that this is equal to about 1.61. And that's a pretty good answer, right? I mean, if we look at this picture, if this is 2, this is 3, this side looks like it could be 1.61. If you get an answer that's negative, or you get an answer that, you know, if this side turned out to be like 100, then probably you've done something wrong, okay? So, but it's good to just check that your answer is realistic. In this case, it is. 1.61 seems reasonable if we've drawn the diagram correctly. Okay, so this is a straightforward law of cosines question. Any questions about it? No, it's clear. Okay. So let me just box the answer. Okay. So so this one is also a law of cosines question, but a little bit less straightforward. So law of cosines here says what? So we have, does a triangle whose side lengths are 6, 8, and 9 have an obtuse angle? So I'm going to draw this triangle. I mean, the way I draw it, it looks like it probably doesn't have an obtuse angle, but I don't know if I'm really drawing it correctly, right? So what we have to do is, again, we're going to use the law of cosines. And one of the things that the law of cosines can do is, if you know all 3 sides of the triangle, remember, law of cosines says c squared equals a squared plus b squared plus 2ab cosine c. So if we know all 3 sides, if we know c and a and b, then we can solve for cosine of c, right? We can solve for cosine of the angle. Actually, yeah, we should, maybe I should spend a day talking about inverse trig functions. So I didn't, maybe we'll do that next week. So we'll talk about inverse trig functions next week. Okay, so the law of cosine. So for instance, if I call these sides A, B, and C, and if I want to calculate angle C, I know, for instance, that plugging everything into the law of cosines, I get that 6 squared equals 8 squared plus 9 squared plus 2 times 8 times 9 times cosine of C. Or in other words, we have that 36 equals 64 plus 81 plus 2 times 8 times 9 is 144 cosine of C. Or what that tells us is that, oh, sorry, minus. Sorry, I wrote this wrong. This should be minus plus b squared minus 2ab cosine of C. And then this here should, I want it to be smaller. Precision eraser, yeah, okay. Okay, I want this to be, this should be a minus 8 squared plus 9 squared minus 2 times 8 times 9, so 64 plus 81 minus 144 cosine C. And what you get here when you simplify this all out is 144 cosine C equals 28 plus 81. It's going to be 109, okay? Or cosine C, so right, that's 145. Yeah, so you get cosine C equals 109 over 144. Now, let's say we didn't have a calculator, right? So I don't know what angle has cosine equal to 109 over 144. But the question isn't asking me to determine every angle, right? The question is just asking, is there an obtuse angle? Remember, an obtuse angle means greater than 90 degrees. So this angle C, its cosine is 109 over 144. That's a positive number. So if I have an obtuse angle, is the cosine of that angle positive or negative? So remember our quadrants here, right? Have our quadrants here with A, S, T, C. So this tells us that in this second quadrant, these are the obtuse angles, right? The acute angles here are in the first quadrant. The obtuse angles are in the second quadrant. And in the second quadrant, only sine is positive. So that means if I have cosine of an obtuse angle, it's going to be negative. So here, if cosine C is positive, so since cosine C is positive, C must be acute. C must be an acute angle. Okay, right? Because if C was obtuse, then its cosine would be negative. So what we see from this is that at least angle C is not obtuse, right? We can use the law of cosines to figure out its cosine, and then we don't even really need to do the calculation. We just need to know whether the cosine is positive or negative. And whether the cosine is positive or negative, that's going to distinguish the acute angles from the obtuse angles. Okay? So we'll do the same thing for the other two angles, but for now, is that clear with how at least angle C is going to be guaranteed to be acute?
It's clear.
Clear. Good. Okay, so let's do with the other angles. So with the law of cosines, you can always change the letters. So now let's say I want to do angle B. Well, I can take the opposite side. That's going to be 8 squared is going to be equal to, so if I'm doing angle B now, I get 8 squared is going to be 6 squared plus 9 squared minus 2 times 6 times 9 cosine of B. So 6 squared plus 9 squared minus 2 times 6 times 9 times cosine of B, right? This is because I have one formula for the law of cosines, but you can also just permute the letters. So B squared in generally can be A squared plus C squared minus 2AC cosine B. That's also just a version of the law of cosines. You've just labeled your triangle differently. So here we have 64 equals 36 plus 81 minus 108 cosine B. And so you add the 108 cosine B to both sides. And if you subtract 64, you're going to get 108 cosine B is equal to going to be 53. Can do the algebra if you want to. And so cosine B is equal to 53 over 108. And again, since cosine B is positive, B must be acute. Okay, so angle C is acute, and angle B is also acute. Okay, exactly the same method. So let's try with angle A now. This is the last one. So we'll try with angle A. I'm just going to redraw the triangle up here. So A, B, C, and this was 9, 8, 6. So for angle A, what we have is that A squared equals B squared plus C squared minus 2BC cosine A. Right? You have the side that you're trying to figure out. That's always going to be the sum of the squares of the other two sides minus 2 times their product times cosine of your angle. So in this case, we have that 9 squared is equal to 6 squared plus 8 squared minus 2 times 6 times 8 times cosine of A, or 81 equals 36 plus 64 minus 96 cosine of A, or that gives us that 96 cosine of A is equal to, this ends up being 19. And then cosine of A is equal to 19 over 96. Okay? And this is still positive. So A is also acute. All right, so what have we seen? We've seen angle A is acute, and on the previous page, we saw that angle B was acute and angle C was acute. And so since all of them are acute, so what did the original question ask? It asked, does a triangle whose sides or lengths are 6, 8, and 9 have an obtuse angle? And the answer is no, right? We checked every angle, and every angle turned out to be acute. Okay. So you can tell just from the sides of a triangle. You don't have to be told the angles. But from the sides of a triangle, you can figure out the angles and you can tell whether they're acute or obtuse. Yes, Abraham?
Yeah. What you have, what we have 64 is equal to 36 plus 81 minus 108. How that 108 tend to be positive?
Oh, because I did this a little fast. The 108, I added 108 cosine B to both sides, so that cancels it out over here, and it adds the 108 cosine B over here to the left side.
Okay.
And then I did a couple of things. So what I really did here was I did plus 108 cosine B on both sides, and then I did minus 64 on both sides. Just for space, I didn't write out every step, but that's what happened here.
All right, thank you.
Okay, you're welcome. Other questions? Okay. Okay. Okay, let me see. Okay, great. All right, so that's it for homework. So this is law of sines and law of cosines. Okay, so I'm going to skip the angle bisector theorem for now because I want to make sure we have enough time to do this exercise that I want to spend the rest of class doing. If we have time at the end, I'll go back to angle bisector, but probably we're going to save this for next week just because we started a little bit late. So I want to make sure that we get to everything else. So we're going to do this next week. Okay. Okay, so we haven't talked about trigonometry, like applications so much of trigonometry. So, there's lots of applications of trigonometry, and some of them have to do with triangles, but a lot of other things don't have to do with triangles. So one of the important things about trigonometry is if you remember your sine curve and your cosine curve, they have this property that they're periodic, right? They repeat themselves over and over again as you move along the x-axis. And what this means is that sines and cosines are very good for modeling things that repeat themselves. And so in particular, lots of things involving the Earth and rotation, the Earth spins around and around and around, or the sun going around the Earth. These are paths that repeat themselves. And it turns out that trigonometry functions are very natural for modeling these kinds of what are called periodic phenomena, the things that repeat themselves. So it's good also for pendulum motion. If you do physics, simple harmonic motion is done in terms of sines and cosines. So I want to talk about a particular application today, which is about predicting sunset and sunrise times for future days. So first, we need to do a little bit of setup. So when we say a generalized cosine curve, what we mean is a graph of this form. So the standard cosine curve would just be y equals cosine of x. And we know how to draw that cosine curve. For a generalized cosine curve, we're allowed to put in these 4 other letters. So it's a slightly more general thing. We say y equals not just cosine x, but a times cosine of bx minus c plus d. Okay? And these constants are just allowed to be any real numbers, but just for simplicity, we're going to assume that a is positive. And you know what? I'm going to also assume that b is positive. That's going to make things a little easier. I'm going to also assume that b is positive. It doesn't really matter because cosine's an odd function. So if b is positive or negative, it kind of makes no difference. But just for simplicity, let's assume b is positive. And note that if our choices are a is 1, b is 1, c is 0, and d is 0, then this is just the standard cosine curve, right? Because in this case, we would have y equals 1 times cosine of 1x minus 0 plus 0, right? This is what we would get with, this is our a, b equals 1, c equals 0, and d equals 0, right? And if we have this, then you just get this, 1 times cosine 1x minus 0, and this simplifies to just cosine of x, right? So the cosine curve is a special case of this more general curve over here, where you're allowed to throw in all of these constants. So what we want to understand first, and we've talked about this a little bit before, is what do these constants do to the curve, right? What do these constants do to the curve? Okay, you know, how does changing them affect the curve? And then, okay, and then what's nice about this is that if we choose these in the right way, then this graph will model a lot of different things. Okay, so let's first talk about the curve, and then we'll talk about what it can model. Okay, so but first of all, any questions about what a generalized cosine curve is, what it means that we're throwing in these constants? Okay. Okay. Okay, great. Okay, so first of all, what happens when we vary a? So I'm gonna write this equation again. Y equals a times cosine of bx minus c plus d. Okay, well, what happens when we vary a? Well, this affects what's called the amplitude of the graph, right? So if we have, y equals cosine of x, that's gonna look something like this. And where this goes from 1 to -1, that's going to be its range. But if we do instead y equals 2 cosine of x, that would be a equals 2. What happens? Well, all of the y values get multiplied by 2. So the graph basically looks the same, but now the range is from 2 down to -2. Okay? So what we see here is, modifying a stretches or compresses, for instance, if we replaced a by 1/2. So stretches or compresses the graph in the vertical direction. Okay, a is not a variable, right? A is a constant here, so to James's question, and so we're using different values for a. So this would be where you have a equals 1, and this would be if you have a equals 2. Right? So one of them you get y equals cosine x, the other one you would get y equals 2 cosine x. So I'm trying to just isolate each quantity here and try to understand what it means. Okay, so what we see is if you replace a, what that does is it multiplies y by that factor a. And so y equals cosine x versus y equals 2 cosine x, the 2 cosine x graph will be twice as long in the vertical direction as the cosine x graph. Okay, so this affects what's called the amplitude of the graph. Okay, so in this case, this would be a equals 1, and by the way, b equals c equals d equals 0. So here we also have b equals c equals d equals 0. Okay, so this is what happens with a. Now, what happens when we vary d? Well, so let's say that I now look at, y equals cosine x plus 1. Right? So in this case, that would correspond to a equals 1, b and c are still 0. Oh, sorry, b equals 1. Sorry, a equals 1, a equals 1, b equals 1, c equals d equals 0. So that's That's y equals cosine of x. And here, this would be also c equals d equals 0 and b equals 1, let's just say. So here, we would have, let me just do this, a equals 1, b equals 1, d equals 1, and c equals 0. So that would correspond to y equals cosine x plus 1. And what happens when we do d, right? So the difference between y equals cosine x plus 1 and y equals cosine x is we add 1 to the y values. So that's not going to stretch, but it's going to shift. It's going to shift the graph up by 1. So if we drew this version of the graph, it's going to be, instead of going from -1 to 1, it's going to move everything up by 1. So it's going to go from 0 to 2. So here's 0 and here's 2, and I'll have a similar kind of cosine graph, but the range is now going to go from 0 to 2. So we have is, so modifying d shifts the graph up or down. Okay, so these are two things that we can that we can change about these generalized cosine graphs. You can change the a, which won't change where the graph is centered, but it'll stretch it or compress it. Or you can change the d, which doesn't stretch or compress, but it does move the graph up or it moves the graph down. No, wait, sorry. Okay, any questions so far? We're just talking about A and D right now. So if you change A, it's a stretch, and if you change D, it's a vertical shift. Okay, so good. So let me say something else here. So what happens with A and D? So what's the maximum Y value that's achieved from the graph? Well, the maximum Y, what's the maximum possible value here? Well, the largest that cosine of anything can be is going to be 1, right? So the largest value that this can take on is going to be A plus D, right? Because the maximum Y value happens when this cosine term is equal to 1, right? That's the biggest cosine can be, is 1. So the maximum total value is going to be A times 1 plus D, right? That's as big as you can get. So the maximum Y value achieved from the graph is going to be A times 1 plus D, or A plus D. Right, so if I have a generalized cosine curve, I'll write the equation down again. So y equals a times cosine of bx minus c plus d. So this thing over here has maximum value 1. And so the total maximum value is going to be a plus d, right? Alternatively, for the minimum value, well, we need to know what's the minimum value. What's the minimum value that you can get by plugging in a certain x? Well, so the minimum value of cosine is -1, right? So that means the minimum value that this whole expression can take on. Remember that a is positive. So the minimum value that this can take on is going to be minus a plus d. So the minimum value is going to be minus a, or well, maybe I'll say the value is going to be a times -1 plus d, or minus a plus d. Okay. And so in particular, here we can solve for a and d, right? Because we would get that so for instance, one way of doing that is we can get that the max plus the minimum value is equal to a plus d plus negative a plus d. and that's going to be equal to 2d. So this gives us that d is equal to the maximum plus the minimum divided by 2. And similarly, if I do max minus min, this is equal to a plus d minus a plus d. And that comes out to be equal to 2a. And from this, we get that a is equal to the max value minus the min value divided by 2. So what's the point here? You know, the point is that if I have some generalized cosine curve and I don't tell you the equation, but I just tell you that it's a generalized cosine curve, and you want to figure out what are the actual values of these constants, what are a, b, c, and d, well, at least for a and d, we can solve, right? If we know what the maximum value that our function takes on is, and we know what the minimum value that it takes on is, then we can solve for d. D is just going to be the maximum plus the minimum divided by 2, the average of the maximum and the minimum, and a is just going to be the maximum minus the minimum divided by 2. Okay, so what we're going to do now is we're going to try to do the same thing for b and c. Okay, so how can we figure out just from looking at the graph what b and c are going to be? Questions?
Yeah, please, the question again.
Yeah, yeah. Any more questions or okay?
Did not hear the question I asked.
No, there are no questions. I didn't hear any questions.
Oh, okay.
No, sorry. Okay. So, okay, what about b and c? So I'm gonna write the general equation again. So y equals a cosine bx minus c plus d. Okay, so what happens when we vary b? So we talked about this a little bit before, that this is going to affect the period of the graph. And what happens when we vary c? Well, this is going to affect what's called the phase shift, which we not really going to talk about too much. But the point is, well, when are you going to have a maximum, right? This achieves its maximum value when bx minus c is equal to 0, or where c equals bx, or in other words, where c over b is equal to x. Okay? So the place where this achieves its maximum value, wherever this graph achieves its maximum value, one of the places that's going to happen is at x equals c over b, whatever that is. And then for b, we can figure out the period of the graph because so basically the point is, remember, let's recall, cosine of x has period 2 pi, right? What that means is that cosine of x is equal to cosine of x plus 2 pi, right? Whenever you add 2 pi, the function just repeats itself. So now, fact here is that cosine of bx has period, the period's actually going to be 2 pi divided by b. And why is this true? Well, cosine of bx, let's say I do cosine of bx, but instead of x, I add 2 pi over b, then cosine of b times x plus 2 pi over b is equal to cosine of bx plus 2 pi when I put it all together, and we know that this is the same thing as cosine of bx. Okay, so what we see is if we look at the function cosine of bx, if I add 2 pi over b to x, then that doesn't affect the function, right? Cosine of b times x plus 2 pi over b is the same thing as cosine of bx. So adding 2 pi over b makes no difference to the function. Okay, so in other words, on this thing, that the period of the graph is going to be 2 pi over b. Okay. So let me just say, okay, so let me just give the summary. Let's say that we're given a generalized cosine curve y equals a cosine bx minus c plus d, but we don't know a, b, c, and d. We're just given the curve. Okay, so somebody says, this is a generalized cosine curve. There's some values that we're using for a, b, c, and d, but I'm not going to tell you what they are. How can you figure it out? Well, we can determine a, b, c, and d using what? Well, a, we saw before, this is going to be the max value minus the min value divided by 2. Okay. B, well, the period is 2 pi over b here, right? So this says that, you know, so if 2 pi over b equals period, then b is equal to 2 pi divided by the period. Right? That's what happens when we solve for b here. Multiply both sides by b and divide both sides by the period. That gives us this b, right? So that tells us that b here is 2 pi divided by the period. Okay. So c, we already mentioned this. So c is going to be equal to, well, whatever x gives you the maximum value, if you multiply that by b, then that's going to be your c, okay? So c is, you know, so is going to be b times the x that gives the maximum value. Okay. And then d, we saw this a couple slides ago, d is just the maximum value plus the minimum value divided by 2. Okay, so basically, if somebody hands you a generalized cosine curve, and you just see the graph, they say, this is a generalized cosine curve, here's its graph. I'm not going to tell you the equation. Well, from its graph, you can figure out what's the maximum value, and what's the minimum value, and what's the period. And once you know the maximum value, and the minimum value, and the period, you just see how fast it repeats itself, then you can use those quantities to solve for a, b, c, and d. Okay? And once you've solved for a, b, c, and d, now you know what the actual equation is. And so you can figure everything out. You can figure out, you know, what is the actual equation that's giving you this graph. Okay? So it's maybe not clear yet why you would want to do this, right? What's going on this, you know? So why would you want to determine these coefficients? Well, let me give the following application. Okay? So it turns out that the number of daylight hours in a given place in a given year can be modeled by a generalized cosine curve, where x represents the day of the year. So x kind of ranges from 1 to 365. So January 1st is 1, January 2 equals 2, all the way up until December 31 equals 365. I guess in this year it's 366, right? Because it's a leap year in 2024. So we'll call it 366. And y is representing the number of daylight hours. But which generalized cosine curve? Well, that's going to depend on where you are, right? The number of daylight hours in Liberia is going to be different from the number of daylight hours in New York, right? It's different and the number of daylight hours at the North Pole is going to be different from the number of daylight hours in South Africa, right? So it's all going to depend on where you are. And so what this means is that you're going to have, you know, y equals a times cosine of bx minus c plus d, where x is equal to the date using this representation here, and y is equal to the number of daylight hours. But every city, every town on the globe is going to have different values for a, b, c, and d. Okay. And so if you want to figure out what those are, so you can figure out what those values are from having the data for the daylight hours for at a given place. So let's do this. We're going to do this for Ganta, and then for homework, you're going to do this for Monrovia. Okay, so what we're saying, if we want to pick the correct generalized cosine curve that actually gives us the right equation, then we need to determine what is A, what is B, what is C, what is D. But we're going to be able to do that because we're going to be able to see the quantities that we need. Remember, the quantities that we need is the maximum daylight hours. We can look that up. The minimum daylight hours, we can look that up. And what is the period? And the period is just 1 year, right? The daylight hours repeat themselves over the course of the year. Okay, so let's do this for Ganta and Monrovia in 2024. Okay, so you can get this data over here. So this is the relevant data. You can go to this website, dateandtime.info, for city sunrise and sunset. So let me show you how we find this. Okay, so let me go put in this link. So HTTPS date and time.info/city sunrise sunset .php $ID equals 2277197. Okay. Oh wait, oops, date and time, not data and time. Okay, so here we are. So this gives us just today what are the sunrise and sunset times in Ganta. But if we want to see more, you have a whole calendar, right? So it says sunrise, sunset, solar noon, which means when's the sun at the apex, and then how long is the day. And it does this in hours and minutes. Okay, so what we want to, and you can change your month, and you can change your year, you can get the sunrise and sunset times for any day. So if we want to determine A and B, we need to know the max and min number of daylight hours. Okay, so the maximum number of daylight hours is going to be something that we can look up. Well, I think it's usually in June, right? So let's see, where's the maximum number of daylight hours? Let's look in June. Yeah, it looks like right over here. So it looks like the longest day of the year is June 20th or June 21st. They're the same, right? And the maximum is 12 hours, 35 minutes, and 8 seconds. So max is equal to 12 hours, 35 minutes, and 8 seconds. And well, we need to convert that into a decimal, right? So 35 minutes equals, well, how much of an hour? So 35 divided by 60, 35 divided by 60 is going to be 0.583 hours. And then 8 seconds is equal to how many hours? That we'd have to do 8 divided by 3,600. So that's going to be 0.002 hours. So the total looks like it's going to be roughly 12.585 hours. Or let's just round, let's round to say 12.59 hours. Yeah, then let's keep it a little more precise. Let's say 12.586 hours. Okay, that's our total maximum daylight time. So what about the minimum total daylight time? We've got to look that up again. So the minimum should be sometime in December, right? So let's look in December. Let's look at December. What's the shortest day? Well, the shortest day here looks like, oh wait, no, I don't want the twilight calendar. Here we are, sunrise and sunset calendar. So the shortest day looks like it's right around here. So like December 20th, December 21st, that's 11 hours, 44 minutes, and 15 seconds. Okay, right, sunset, sunrise, sunset, solar noon, and day length. So the minimum is going to be 11 hours, 44 minutes, and 15 seconds. So again, let's convert this into a decimal. So for a decimal, I need to do, so 44 divided by 60. So 44 minutes equals 0.73 hours and 15 seconds. I do 15 divided by 3,600. So 15 seconds is equal to roughly 0.00, let's say 0042 hours. Okay, and so altogether, the total is going to be, you know, about, let's say 11.737 hours. Okay. Let's say that's our maximum and what's our minimum. Okay. And so what we're going to get is that A, remember, is equal to the max minus the minimum divided by 2. And that's going to be what? That's, oops, wait, sorry. Max minus the minimum divided by 2. So that's going to be, oh, sorry, let me share my screen again. Okay. Oh, and let me just record one other thing. So maybe before I do this, let me record one other thing, which is the longest day, which was back in June. So the longest day, which was back in June. So the longest day we had right here is between June 20th and June 21st. So the max is achieved on June 20th/21st. So what day of the year is that? I'm just going to do a quick count. So 31 for January, 29 for February is 60, 31 for March is 91, 30 for April is 121, 31 for May is 152, and then we add, let's say, another 20.5 days. So that's going to be, we're going to call that 172.5. So this is the day of the year. Right, so this is on the 172.5th day of the year, which is going to be, you know, the average of June 20th and June 21st, which are these two longest days. Okay, so this is everything that we need in order to figure stuff out. Okay, so let me turn off. Let me stop my share. Let me share my screen again so that you can see what I'm writing down. So let me go to share. Okay, share my screen. Okay, so here's the data that I wrote down from the website. So I said the maximum length was 12 hours, 35 minutes, 8 seconds. That turned out to be converting everything to decimals. So 35 minutes was this many hours, 8 seconds was this many hours. So converting it all to decimals was going to be about 12.586 hours. And then doing the same thing for the minimum, which was 11 hours, 44 minutes, 15 seconds. And we converted everything to decimals. And so the minimum length of a day was 11.737 hours. And then we also saw that the maximum was achieved on June 20th, 21st. So that was on the 172.5 day of the year. Okay. And then lastly, we have the period, which actually, the actual period for when the sun goes around the earth, how long is the length? The period is actually roughly 365 1/4 days. And that's why we have a leap year every 4 years. So this would be a good enough approximation for now. So it's 365.25. It's actually a little bit less than that, but that'll be a good approximation for now. Okay. So from this information, we can determine all of the quantities that we want. So let me bring a new page. So so what do we have? Well, remember our equations. So A was equal to max minus min divided by 2. So from our previous page, the max was 12.586 and the minimum was 11.737. So we have 12.586 minus 11.737 divided by 2. That is 2.586 minus 1.737. So this becomes 0.849. Okay, so that's A. So D was the same thing, but with the sum. So this is max plus min over 2, which is 12.586 plus 11.737 divided by 2. Oh, sorry. Oh, we had to divide by 2. Sorry, I didn't divide this by 2. Sorry, that's 0.8. What did I just do? No. Sorry. I need to do this divided by 2. Sorry. So that's 0.24245. Let me erase that. Okay. So that's 0.4245. Sorry about that. So now I do the same thing, but with a plus instead. So that's going to be 12.1615. Now, B, if you recall our formula, is equal to 2 pi divided by the period. And so that's 2 pi divided by 365.25. So I'll just do that. You just type it into a browser. It's going to know 2 pi divided by 365.25. That's going to be equal to 0.0172. And lastly, C, what was the formula? So the formula for C, let's go back. C was B times the X that gives the max value. And we saw that the X giving the maximum value is 172.5, right? This is the X value giving the maximum Y value. Okay, so that's going to be 172.5. Okay, so C here is X value giving the max Y value, and that's going to be 172.5. Okay, so what we see is that the function modeling number of daylight hours in Ganta is y equals, so 0.4245 times cosine of bx minus c, so 0.0172x minus c, which is 172.5, and then plus d, so plus 12.1615. Okay, so this is the function. Okay. This is the function. We're here, remember, y equals number of daylight hours. And x equals the date, right? Given by 1 is January 1st, 2 is January 2nd, and so on. Okay, so this has gone to at least in 2024. Okay. So this is kind of cool, right? We take only a few data points, just the maximum and the min, and when is the minimum achieved, and we can come up with a function that tells us exactly what the number of daylight hours, or not exactly, but it gives us a very good approximation to what the number of daylight hours is in Ganta on any given day. So the last thing I want to do today is just graph this so that we can see what this looks like on a graph. So let me do a graph. I'm going to do Desmos here. So let's try this. So let me graph desmos.com. Okay, graphing calculator. Wait, no. Let's go back to GoodNotes. Yeah, okay. So I'm going to do this. Y equals 0.4245 times cosine of 0.0172 times x minus 172.5, okay, and then plus 12.1615. This is the function that we have. And now this isn't going to look like very much, but that's because we have to look at where the graph actually lies, right? So this, I want to see if I can somehow put in the range. So I would love to go give a range. I should have, can I change the range and can I change the, no, I want to pick the range. No, let me try GeoGebra. Let me try graphing on GeoGebra. This might be better. No, wait. GeoGebra. Let's try this. Can I put in the range? Let's see this Desmos pick range. Restricting domain and range. Okay, here we are. Blah, 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 blah. Define the domain. Oh, okay, so add this phrase. Sorry, I'm just looking up. I should have figured this out beforehand. Okay, so view the graph. What is the domain restricted to? Okay, so you put this in. Okay. Okay, let me try this again. Let me try this again. Let me try this again. Let's see if this is going to work. Okay, so I'm going to do the same thing. So y equals 0.4245 times cosine of 0.0172 x minus 172.5 plus 12.1615, and I want to say 11 less than y less than 13. So let's see what happens if I do that. Okay. You know what? I think I'm not going to be able to figure this out today. So let me promise this to you for next week. We'll see what the graph looks like. Yeah, maybe I'll do that next week. We'll see what the graph looks like. Let me just share my screen again because we're just about done. Okay. So I'm going to show you what the graph looks like next week, okay? Because I want to be able to graph it nicely and figure out how the website works. So we're going to do the graph next week. Okay, and so the homework exercise is to try to carry out the same thing for Monrovia instead of Ganta. And you're going to get a slightly different answer. It won't be that different because the number of daylight hours in Monrovia versus Ganta is not that different because they're not that far from each other. But what I want you to do is write a generalized cosine curve that gives the number y of daylight hours in Monrovia in 2024 as a function of the date x. And if you want to, you can use this website. This is what's going to give you the data for Monrovia that we got from Ganta. And so remember, to go back, what do you have to do? You have to figure out what's the maximum amount of daylight. You have to figure out what's the minimum amount of daylight. You have to figure out what day of the year gives you the maximum amount of daylight. And then you have the period, which is still going to be 365.25. Okay, the period's not going to be any different. That's just how long a year is. And from that, you can figure out what A, D, B, and C are going to be using these formulas. And in the end, you get an equation for this generalized cosine curve that's going to be a little bit different than the equation that you got for Ganta. Okay? So we'll go over this next time to try to see what you can do for Monrovia. And again, you can get the data for Monrovia here. I'll send out the I'll send out the slides so that you can see what the website link is. Okay? And so next time, this is actually not what we're going to do. We're going to discuss the angle bisector theorem, and inverse trigonometry functions. Okay, we'll save complex numbers for later. And next week, we will go back to meeting at the usual time of 4:30. Okay, so we're not going to meet at 2:30 next week. We'll be back to meeting at 4:30. So sorry about the change today. I know it's always a little bit challenging when there's a change, but thank you in the end for everybody showing up. And remember to put your name in the chat if you haven't done so yet. And I will stop the recording in a minute. I do have to go in a minute, but any last questions?
Andrew?
Yes. Aby?
Yes, Abraham.
Yeah.
Yeah.
Hi,
Oh,
Aby.
thank you for the class today. Yeah, number. Thank you for the class today.
You're welcome.
And we hope that all the teachers will be able to be in class for next week. I know today was a day change, and maybe most of them did not really come on time. But hopefully that next week most of them will be able to come on time. And we're going to be having meeting with our math teacher then tomorrow in Ganta, getting prepared for the competition.
Competition, yes. I'm gonna send the funds over today.
Yeah. So thank you very much.
Okay.
We hope that we'll continue working hard. Thank you.
All right. You're welcome.